And I think you know, a lot of you have been coming to 60 Minutes in Space programs, and for those of you who've at least been to the last several, you know that I've been experimenting. Okay, it's back again. And the way that we're doing it is I will actually be posting a QR code at the end of the talk tonight, and you can submit your questions to me. And last month, I actually answered 3 different questions from people who had submitted questions. I think it was 3. This month, I'll only be using one of the questions that someone had submitted to help advance the presentations tonight. But if you have a question about anything involving space or astronomy, and if you don't want to ask it tonight after we go into Q&A, definitely you know, wait for the QR code at the end, and you will have your opportunity to ask me a question. And so with that, I'm going to go ahead and jump in. But one final thing that I just wanted to point out is that, well, I'm Chun, and I'm the Curator of Space Science here at the museum. And my background is in astronomy or astrophysics. And so, so for the most part, when I do 60 Minutes in Space programs, I'll be talking about things outside of our solar system for the most part. And then every now and then, I might break from that. And so at the very end, I'll actually only be doing 2 stories, but at the very end, you'll find an example of that. So with that, let's go ahead and get into our program. And the question from the audience that was submitted last month was, how is the distance of a star from Earth determined? And that's from Isaac. And in order to answer this question, I'm actually going to, I mean, not only answer this, it turns out that there are lots of ways in which you can figure out distances to stars and other objects in the universe, but we're going to focus on the way that people, astronomers have been doing for well over 100 years, and apply that to a black hole. So we'll be talking about black holes for this particular story. And in order to get into the details of the story, I'm going to be talking about the Gaia satellite, which is a satellite that was launched by the European Space Agency. And the Gaia satellite was able to produce this all-sky map. So imagine the entire sky, 360 degrees around in multiple directions. And if you flatten that into this projection, this is what you would get. And so here we're seeing the Milky Way. And let's see if I can get this to show up. It's sort of showing up. And so if you, there we go. Let's see. But what we're seeing are not just stars, but stars observed by the Gaia satellite. And so the Gaia satellite observed the nighttime sky and very accurately determined the positions of all these stars. And so these dark regions, which we know to be gas clouds in the Milky Way, they're not dark in this image because we're actually seeing gas clouds, but it's because Gaia isn't seeing any stars in those regions. So those dark regions are the absence of stars. And then we also see the large and small Magellanic Clouds. These are smaller satellite galaxies that we can only see in the southern hemisphere. And so the way that Gaia works is through the process of parallax. And for those of you, I mean, you might have done this. You can even do this right now. If you stick your thumb out in front of your face and you look at your thumb using either eye, you'll notice that your thumb or finger seems to move against the background. And I went upstairs to our sky terrace today and took a couple of pictures. There were volunteers up there who had set up solar viewing telescopes. And so if you look at these 2 pictures taken from slightly different positions on the deck, you can see those telescopes move relative to the background, which is the skyline or the mountains in the back there. And if we actually try to measure or figure out where these telescopes are relative to the skyline by the red bar, the yellow bar, and then this yellow, or the orange bar, and this yellow bar is supposed to correspond to this corner of the sign. And we do the same. You can see that everything has moved relative to the background. And if we now actually look at how far, you can see that the furthest telescope has moved not quite that far relative to the background. The nearer telescope has switched positions a little bit further. And then finally, the sign, which is the closest object to us, has flipped or moved relative to the background the most amount. And so that's basically how parallax works. If you are looking at something in the foreground and you're comparing it to something in the background, you're basically watching how much it appears to shift as you yourself shift. So how does this work in astronomy? Well, instead of having telescopes on the Earth shift their position, I mean, that's kind of hard to do because telescopes are usually fixed. But what we can do is we can measure or make observations when the telescope is on opposite sides of the sun. And so instead of having a baseline or you shifting the telescope a few miles or across the surface of the Earth, now you're using the size of the solar system, the Earth's orbit, to help you create this parallax effect. And the Gaia satellite is in orbit around the Earth. And so as the Earth orbits the sun, the satellite will be seeing closer foreground objects shift relative to the background. And here is just a simulation of how that would look. And so if nothing was in motion, this is what you would see. So this is obviously a much closer star because it's going around in a bigger circle, whereas this star is a lot further away. It's moving in a smaller circle. Now, it looks brighter because that further star is actually brighter. And so let's see if we can see that again. So stars have different brightnesses, and you can't use the fact that one star appears to be brighter to tell you how far away it is. But you can use, again, if you were to measure these stars over time, you can use the fact that they appear to be moving in circles or shifting by different amounts to give you an idea of how far away they are. Now, stars aren't static in the sky. They actually have very small motions due to the fact that our sun is in orbit around the galaxy and all these stars are as well. And so instead of just circles, you actually get these spiral patterns. And again, the amount of motion and the type of motion depends on how far away they are, and then also how fast they're moving relative to us. And so I'm going to switch topics from parallax to talking about black holes. And black holes, I think, are one of everyone's favorite topics. I get asked about it all the time, but this is the first time that I've actually kind of jumped in and looked at how we first observed black holes. And it turns out that even though theoretically physicists have been wondering whether black holes existed or not ever since Einstein, or soon after Einstein had published his general theory of relativity, the confirming evidence for their existence didn't come until about 50 years ago, so in 1972. And it was first published in Nature by an astronomer, Tom Bolton. And so he realized that his observations show that this X-ray source in Cygnus, or Cygnus X1, was associated with this star. And it appeared that a black hole was in fact in orbit around the star. And basically, the idea is that black holes are very difficult to observe because they're so small, they're so compact. But despite the fact that we think of them as not emitting any light, they do have emission. And when this happens, when a black hole is in a binary system with another star. And so you might, many stars in the nighttime sky are in orbit around other stars. They're in either binaries or in triples or even larger n-tuples of stars. And for massive stars that are greater than 8 times the mass of the sun, they blow up in supernova. And depending on how much matter is left over after they blow up, the collapsing remnant of the star can actually turn into a black hole. And so if you have a massive star destroy itself at the end of its life, it turns into a black hole. And normally, because there's nothing that would emit from the black hole, you wouldn't be able to see it. But if it was in orbit around a second star, then what can happen is that the outer envelope of that second star can fall into the black hole. But before it does so, it falls into what's known as an accretion disk, and the gas from that second star will slowly spiral in. But the gas gets jammed up, and so it heats up from friction, and this can result in the gas being heated up to millions to tens of millions of degrees. When you have gas that hot, it actually emits in X-rays. And so our first evidence of black holes came from transients, meaning emission of light or X-rays that appeared spontaneously and then it disappeared, and it didn't necessarily repeat again. And so, over time, astronomers were able to actually identify systems that were binary systems that appeared where we could see one star, but there appeared to be a hidden binary object or a second object that we couldn't see, but every now and then we would have these transient X-rays. And so that was evidence that there was gas falling in, that gas was getting heated up to millions of degrees, and that showed up as X-rays. And so this first example of Cygnus X1 was confirmed to be a black hole more than 50 years ago. But just 3 years ago, there was a new paper that came out to show, based on newer observations, to show, actually, it also turns out to be one of the largest black holes in our galaxy that we know of. So it turns out, so here's a comparison of our sun. It turns out that Cygnus X1 is about over 20 times the mass of our sun. The other star, so this blue star off the image, or off the display here, is about 40 times the mass of our sun, but diameter-wise, it's only about 22 times. So we have these two massive stars that are in orbit around each other, one of whom turned into a black hole, and we learned about it because of the X-rays that it emits. Now this is from a paper from 8 years ago, and the paper was from a group of authors who decided to go into the scientific literature to look up all the papers and all the discoveries that have been made for black holes. So you can see it goes back to the late 60s, and back then there was only a single, if you count, this is 0, so there's only one object known in the late 60s. And since then, there really haven't been that many black holes that have been discovered in our galaxy. And this only goes up to 2016, but even though, so let me explain what the two colors mean. So each of these names corresponds to a different X-ray satellite. So it turns out that when we've put up X-ray satellites, these satellites can detect transient X-ray sources, and so that's how we've really discovered the vast majority, if not all, of the black holes. It's from these binary systems, from the transient X-rays. But these X-ray satellites aren't necessarily, they don't necessarily have the resolution to actually pinpoint where the star that is associated with the black hole binary, the actual visible star, the star that's losing its outer envelope to the black hole. So even though you have increasing numbers of red, and so you can imagine that 8 years later, we're probably at 70 or 80 black holes discovered, or black hole transients. That's what the BHT stands for. But in order to actually identify the orbiting binary pair, you have to be able to nail down the star, and you have to actually observe it very carefully to be able to detect its motions. And so that's what these blue lines in the histogram are. They represent how many of these stars have actually gone through this exercise where astronomers have taken a really close look to determine the orbits of those pairs of stars. And so you can see, it's been stuck at just below 20 for a while, and the numbers have been around 20 or a little bit more, but there haven't been that many more dynamically discovered black holes. So that's the blue. And I think, let's see, we'll just keep on going. And so here is that other paper that I mentioned from a few years ago, where they really nailed down some of the properties of Cygnus X1. And what they did was they used very accurate radio telescopes, or a whole bunch of telescopes stringed together to actually map the emission from the jet and the accretion disk of the black hole. So you can see that they're big error bars, but they're able to show that they correspond to the sort of circular or orbital motion of the black hole. So we get to this most recent paper, which literally just came out in the last couple weeks, and it's called Discovery of a Dormant 33 Solar Mass Black Hole in Pre-Release Gaia Astrometry. So it's using the Gaia data that really accurately determines the position and distance of stars. And the paper's by this Italian author, Panuzzo. But if you actually look at the list of authors, there's actually a couple hundred of them. So he's just the first author. And this is part of the Gaia team. So the Gaia satellites run by the European Space Agency, and there are literally hundreds of astronomers, thousands of other support staff that are involved with the Gaia satellite. So this is why this paper has so many authors, because they have to credit everyone, a lot of people that were involved with this particular mission. All right, so here is what they observed. And so here is the motion. Those dots represent the positions of the star, so the observable star, not the black hole, but the star that's in orbit, that the black hole and the star are orbiting each other. And so you can see that Gaia was able to observe quite a lot of positions for the star. And this red dashed line is what the trajectory of the star across the sky would be if if there was only one object associated with that star. So if the fact that you have this wavy motion is due to the fact that the Earth is orbiting around the sun. So that's the parallax effect that we're talking about. And the fact that it's stretched out has to do with the fact that the sun is in orbit around the galaxy, and the star is also in orbit around the galaxy. So instead of tight little circles, you get this kind of stretched out line. So you can see that they try to match the positions of 3 of those points, but the red dashes don't really line up with the rest of the dots, with the rest of the observations. But if they instead of just having a single star, they put in a binary star model so that there are actually 2 objects in orbit around each other, you can actually come up with a model that will fit all these all the dots. So that tells you that this is probably a binary object. There are 2 objects in orbit, even though we only see 1 object. Here is them making a plot of the star over the course of the orbit. And so here they've taken out the effects of the Earth in orbit around the sun. So we've removed that effect, and now we're only seeing the orbit of that star around this barycenter. So that's the center of gravity of where that cross is. And there's also an animation that they made showing the star and the Gaia observations over the course of its orbit. And this other plot here shows the velocity. So what we're seeing is the star passing through the closest passage point, and this big black dot is actually the black hole. And so the black hole itself is in orbit around the center of gravity. And as you can see, not only do the positions match up, but the expected velocities of the star also match up as it moves in its orbit. So at certain points, it's moving towards us, and then at other points in its orbit, it's moving away from us. So if we go back to the Black Cat catalog, they actually have this nice plot showing all of a lot of the neutron stars that have been discovered so far, and or known masses for the neutron stars. And again, in order to know the masses, you need them to be in binary systems, because you have to use the fact that they're in orbit around something else, or there are two objects orbiting each other for you to be able to determine the mass. And so what's really interesting is that there's a limit. So neutron stars are another end stage of stellar evolution, and neutron stars actually have a maximum mass, or maximum size. And it turns out to be right about 3 solar masses. And so most of the neutron stars that we've discovered are under 3 solar masses. And then if you look at the black holes, they are all definitely above that 3 solar mass limits. So they can't be neutron stars because they're too massive. And the arrows here are just lower limits. So there's a lot of uncertainty about the masses of these objects, but we just know that they're greater than the left edge of each of these arrows. But for the most part, you can see that the masses of the black holes are right around 10 or less. I mean, there's this one that has this enormous error bar, GRO J0422, but for the most part, even if you look at the center of the error bar, it's somewhere around close to 10. And so where does that leave us if we look at the new observations? And so in order to add those to this diagram, we have to expand this plot. And it turns out that before this discovery, there are actually 2 other black holes that were discovered with Gaia. Again, using the same process where they went and looked for wiggles in the positions of the stars. And so Gaia BH1 and Gaia BH2, they're also right around 10 solar masses, so they fall into, they clump up with the rest of these other black holes. Cygnus X1 is over 20 solar masses, so it's way off at the end. And then finally, as we saw in the title of the paper, Gaia BH3, which is this newly discovered black hole, is at 33 solar masses. So it's not only the biggest, most massive black hole that we think originates from the death of a star. So that's that's a very particular type of way to categorize them, just because there are much more massive black holes that are at the centers of galaxies, but they probably ended up the way they were via a different mechanism. So they didn't necessarily start out as a massive star. And so this is the largest black hole that originated as a star that we know of. And it's also relatively close by as well. So it's about, I think, 2,000 light years away. So here's just a comparison of the orbits of the 2 earlier discovered Gaia black holes. So you can tell that they orbit a lot closer, whereas Gaia BH3 has an orbit that takes it roughly to Jupiter's orbit when it's close in, but when it's further away, it's about roughly the distance between the Sun and Neptune. So that system would definitely fit in our solar system, but it's definitely further out than some of these other black holes. And so here's just a video showing the Gaia satellite, and then we'll see where the BH3 black hole is. So the satellite actually has a span in order to make its observations. So the cameras are actually right here as it spans. And the black hole is actually towards the galactic center. It's in the constellation of Aquila, the Eagle. And like I said, it's just under 2,000 light years away. So now we're going to fly through the catalog of stars that were mapped by Gaia. And now we see the system as the one star orbits around the center of gravity, and the black hole will also be orbiting around the center of gravity. And off in the top corner, you see the years, so we're actually advancing really quickly. And this smaller orbit is actually about the size of, or maybe slightly smaller than Mercury's orbit around the sun. So this again is, this is a pretty small orbit. And we're going to keep moving around. So it orbits about once every 11.5 years. And here we're seeing, again, the distances. And one of the things that they discovered about the star is that it's deficient in heavy elements. So we know that heavy elements are created from stellar evolution. Stars will send out elements that they create. And so in this case, this particular giant star doesn't have that many heavy elements, and we can presume that the black hole doesn't as well. And when we look at observations of much more of black holes from gravity wave experiments, it turns out that theoretically they also seem to be deficient in heavy elements. Okay, here is just a look at the orbit of this system. So even though it looks like it's in the plane of our galaxy, when they examine the velocity and the motion of this pair, it turns out that they're actually orbiting well outside of the galactic plane. So the vast majority of stars in our Milky Way galaxy lie in the disk of the Milky Way, but this appears to be part of a system that might have merged with the Milky Way galaxy 8 billion years ago, and so it instead orbits high or well outside of the plane of the Milky Way. So so that might also explain why it's deficient in metals, because it didn't have the same history as the gas and dust in the rest of the Milky Way. All right, so with that, I'm going to go on to our next story, which is about brown dwarfs. And specifically, last week, there was a paper that came out in Nature about James Webb Space Telescope observations of 2 brown dwarfs. And it turns out that this brown dwarf, the reason why it was remarkable is that it emitted, or there's light coming from methane molecules from the atmosphere of one of the brown dwarfs. And I'll explain why that's important. But let's talk about what brown dwarfs are. So brown dwarfs are basically a class of objects that's in between planets and stars. So we know that stars come in all sizes, a range of different sizes. In our sun, we typically think of as like a medium size star, medium mass star. And it turns out that as you go to lower and lower mass of stars, the smaller they are, and also the redder they are. They don't produce as much energy. They're cooler temperature-wise. And so here at the bottom, we have the sun and a red dwarf star. So the sun's at about 5,800 degrees Kelvin, above absolute zero. The red dwarf star, Gliese 229a, is about 3,600 degrees. So that's a lot cooler, and as a result, it looks a lot redder. And at the far end, we have the planet Jupiter. And it looks like I have a mistake, because this should have been truncated before Jupiter. So Jupiter isn't a brown dwarf. That's a mistake on my part. But those 3 smaller middle objects are brown dwarfs, and they correspond to objects that are anywhere between 13 times to 80 times the mass of Jupiter. Okay? So you might ask, so what makes brown dwarfs as opposed to a star or as opposed to a planet? And well, on the star end, at the stellar end, brown dwarfs cannot have normal nuclear fusion, where hydrogen fuses into helium, which is what produces energy in regular stars. So even for the lowest mass stars, you still have nuclear fusion, taking ordinary hydrogen and fusing it into helium and producing energy. But brown dwarfs don't do that, but they do do something known as deuterium fusion. So deuterium is a heavier form of hydrogen, and what happens is that there's enough matter in these brown dwarfs that there's a lot of pressure that weighs down on the center of the cores of the brown dwarfs. And so that pressure is enough to raise the temperature that can cause deuterium to fuse, but it doesn't create enough, as much energy as regular hydrogen fusion. And so what happens is that when these brown dwarfs form, they collapse out of molecular clouds of gas and dust, mostly hydrogen, some helium, and then a small smidgen of all the other elements in the universe. And then over time, as they collapse into their spherical shapes, these brown dwarfs will fuse deuterium at their centers because it's hot enough and dense, the pressure is high enough for deuterium fusing to occur, and that keeps them somewhat heated, but it's not enough for to keep the energy production going so that they would ignite to fuse regular hydrogen. And so over time, the brown dwarfs will just slowly cool and get darker and darker. So initially, you might have a brown dwarf like Theta 1, which is 2,600 degrees, and it's so hot because it's relatively young, and there's still a lot of heat from formation, and there's heat from the deuterium fusion. But over time, and Theta 1 is thought to be about 55 Jupiter masses, but over time it will slowly cool, and Gliese 229b is an example of a brown dwarf that's just under 1,000 degrees Kelvin, and so it's a lot cooler. It's also thought to be older than Theta 1, and then finally, as you get to an even older brown dwarf, WISE 1828, now you're dealing with something that's really cool, maybe a few hundred degrees Kelvin. And at this rate, these are temperatures that are close to room temperature. Room temperature here on Earth is close to 300 degrees Kelvin. So these are objects that are at temperatures that we are familiar with. And then finally, the difference between planets and brown dwarfs is that planets do not have deuterium fusion or deuterium burning. And just because they're too small for the centers of planets to be hot enough and to be dense enough for deuterium burning to occur. All right, so the first brown dwarf that was discovered is actually Gliese 229b, and it was discovered by astronomers at Caltech who used the 60-inch telescope at Mount Palomar in California. And they had a special instrument called a coronagraph, which helped block out the light from the central star. So Gliese 229b is in orbit around Gliese 229a, which is the central star. So whenever astronomers find an object in orbit around something else, like a planet or a brown dwarf, they just add the small letter b. So it's not very imaginative, but that's what they do. And so this is what the ground-based observation looks like. So you can see, it took them a lot of effort to get that observation, and it took them also an additional year for them to confirm that this object was actually in orbit around the other one, because it might be that you just happen to be looking at a background object, something that's a lot further away, that happens to be in the same direction in the sky. So what they did was they waited some time, and then took the observations again. And like I said earlier, stars do have this proper motion. They appear to move in the sky because of orbital motions in our galaxy. Well, when they made the observation the following year, both A and B appear to be moving in the same direction in the sky. So that's really good evidence that these two objects are connected somehow, that they're in orbit around each other. So this is the ground-based telescope image. This is the Hubble Space Telescope image that was taken soon after, and by the same group of astronomers. And here they didn't even bother with the special coronagraph or anything to block the sunlight. The Hubble optics are so good that there wasn't enough scattered light for to drown out the light from Gliese 229b. So that was the first confirmed brown dwarf. So that was discovered almost 30 years ago in 1995. And since then, we've had more than 1,000 brown dwarfs, maybe 2,000 now. I'm not a brown dwarf expert. But this is what the spectra looks like for 229b. And so when astronomers really want to learn about what makes up an object, characteristics of an object, they don't just take a picture of it. What they do is they take the light from that object and they put it through an instrument called a spectrograph, which spreads the light out into its different colors. And once you spread it out, you can actually finger point or identify the elements, the molecules that make up that object, because those different elements and those different molecules can actually absorb as well as emit light, depending on the physics that are involved. And so in this case, this top line, or set of lines, are from Gliese 229b, and this part of the spectrum is roughly in the optical, and the rest of this is towards the infrared. And what they identified is that there are a bunch of features here. You can see these dips, and there are also dips here. So the dips are identified by those vertical lines, and those are associated with methane. And it turns out that these particular features are similar to what you'd find for Jupiter. So the second set of lines down here are the spectra for Jupiter, and Jupiter also has very similar lines or absorption features at those same wavelengths associated with methane. So what this is saying is that this object is cool enough for methane to exist in the atmosphere. So normally if you have a star, perhaps there is methane in the cloud that the star collapsed to form the star, but the temperatures in stars are so hot, thousands of degrees, that molecules like methane don't survive for very long. And so in order for you to see methane in the atmosphere or something, it has to be cool enough for methane to survive. So in this case, Gliese 229b, they realized it was a cool object. Perhaps not as cool as Jupiter, but definitely very cool. And when in a later paper done a few years later, and this is a more complete spectrum, so going from the infrared all the way into the visible part of the spectrum, not only were they able to identify methane, which is CH4, but they also saw evidence for water, that's H2O, cesium, and even carbon monoxide, CO. So again, these are all, especially water, that's again something else that you would expect to survive in an atmosphere if the atmosphere was relatively cool. All right, so that takes us to this paper by Jackie Faraday at the American Museum of Natural History in New York. And so she led a team of astronomers that is in the process of making James Webb Space Telescope observations of lots of different brown dwarfs. But they wrote a paper specifically on two brown dwarfs that they called W1935 and W2220. And these are relatively close by objects, so 47 light years, 34 light years. And that's because brown dwarfs are so small and so faint that almost all of them that you can observe easily tend to be relatively close by. So you're not going to be observing brown dwarfs in another galaxy, but we can observe them close by. There is a lot of uncertainty about how old they are and how big they are, because these are brown dwarfs that are actually isolated brown dwarfs. So they're not in orbit around another star. They're actually free floaters. They're just floating in space. Based on their observations, it appears that they're about 400 degrees, so definitely not room temperature, but these are temperatures that you'd be able to recreate in your oven, for instance, at home. And here is the spectra of the two brown dwarfs. The blue is W1935. The white spectrum is W2220. And the James Webb Space Telescope operates in the infrared. So all these lines are in the infrared. And what's really interesting is that we're zooming into this part of the spectrum over here, so just a small part of it. And you can see that W1935, the lines are actually emitting. So they're actually bright emission lines instead of absorption lines. So normally, if you have an atmosphere that has methane, the methane molecules will absorb out the light at the set of wavelengths in this part of the electromagnetic spectrum. But in this case, this particular brown dwarf is actually bright in that part of the spectrum. So it's not absorbing light, it's actually emitting light. So how is it that a brown dwarf is emitting light? That means the methane must be excited in some way in order for it to emit light. And in our solar system, we can actually get methane emission. And so here is an example of Jupiter and Saturn. And the way that you can get them to emit light is if there are aurora on these worlds. And so it turns out that, we have observed aurora on Jupiter and Saturn. And for the most part, it's from radiation from the sun that is impacting. So the same way that aurora happened here on Earth, we have radiation, either particles or UV radiation that impacts the molecules in the atmosphere. They light up, and they're visible as in the ultraviolet as aurora. And it turns out that there's actually another way that aurora can happen. Now, remember what I said, aurora occur mostly from sunlight or from radiation from the sun. But these brown dwarfs, they aren't in orbit around any star. So there's actually no source of starlight or sunlight that could create aurora. So how is it that you can have aurora on these brown dwarfs? Well, there's another mechanism. So it turns out that in Jupiter, there's actually what's known as a plasma torus around Jupiter. And what happens is Io is a very volcanic moon around Jupiter. So it's spewing material out into Jupiter's orbit. And that material, those gases, get ionized into this donut of gas, of ionized gas called the plasma torus. And some of that gas can fall into Jupiter itself following Jupiter's magnetic field lines. And so the Io plasma torus is something that planetary scientists actually have been observing for many decades now, since the 1980s. Here is an observation showing how this magnetic flux line actually ends up lighting up part of Jupiter's atmosphere. And there are similar spots from Ganymede and Europa as well. And we can actually follow these as these moons orbit around Jupiter. So you can, these spots actually move as they orbit because those spots correspond to the location of each of those moons. So what is really interesting now is that these observations, the methane emission from that particular brown dwarf, it's not a slam dunk yet, but it could be evidence for a moon that's in orbit around the brown dwarf, a volcanic moon that's emitting a material just like Io is around Jupiter, and that somehow those gases are ionized to the point where they're slamming into the atmosphere, the upper atmosphere of the brown dwarf, and it's emitting in methane that we're observing. So pretty amazing results from spectroscopy, or just looking at the light. All right, I'm going to just end with my one non-astronomical, non-astrophysical topic, and that is, of course, the total solar eclipse. And how many of you saw the eclipse? Okay, a lot of people. How many of you actually saw the total solar eclipse? Okay, so we have a smaller fraction. So you've probably had to be in a cave for the last several months not to have heard about the total solar eclipse. And this is the last major one across North America for the next 20 years. And this was very remarkable just because it went across a lot of major metropolitan areas, like in Indianapolis or Dallas and Austin, and even Montreal. People in Montreal saw it. And for those of you who have never seen a total solar eclipse and you've only seen a partial, just know that it's a totally different experience. It's so unlike anything that you've experienced before in your life, just because the pattern of the light is so different. And I was actually on a beach in Mexico, and actually, looks like I didn't manage to save the PowerPoint, so you don't get to see what the transition to totality looks like. But what I wanted to do was to there have been a lot of pictures that people have posted about the solar eclipse, and what I want to do is just to end on some unusual pictures of the solar eclipse that you might not have seen, that aren't of the ordinary sort that you would find being posted by people who were along the eclipse path. So the first one is from Hawaii, from the National Solar Observatory, the Daniel Inouye Solar Telescope. And solar telescopes spend all their time looking at the sun. And in this case, this is actually a 4-meter telescope, which is a really big telescope. And they don't need that collecting area to collect light from the sun because the sun is plenty bright. But the larger the mirror that you have, the finer the detail that you can see. And so they posted this video of the partial eclipse. So Hawaii didn't see a total solar eclipse, but they did see a partial. And this is what it looked like with a limb or the edge of the moon transitioning across the sun. And so you can see these convection cells. So at high enough detail, the sun is just boiling with these cells of activity across the surface. And then you can also see that the limb or the edge of the moon is not perfectly straight or smooth. You're actually seeing the mountains and the craters on the moon that are being highlighted by the sun. Astronauts on board the International Space Station also saw the total solar eclipse. And so this was them passing over when the eclipse was leaving New York and on its way towards Newfoundland as it made its, we're kind of at the end of the eclipse. This was from the GOES-16 weather satellite that's operated by NASA and NOAA. And so here, the satellite is positioned over one spot over the Earth. And here we can see the eclipse being captured by a weather satellite. And finally, the very last, looks like I also didn't have the very last example. But the last one was from the Lunar Reconnaissance Orbiter, which is a satellite orbiting the moon. And so unfortunately, that didn't copy over as well. So with that, we're right at 8 o'clock, and I'm happy to answer questions. But for those of you who are interested, here is the QR code where you can submit a question to me that could be answered next month at our next 60 Minutes in Space. And so we hold these events on the last Wednesday of each month. So our next one will be May 29th, and I encourage everyone to come back for that. And if you have to leave, feel free to do so, but I will be happy to answer questions from everyone. Thanks. Okay, yes, a question.
So for a black hole, when you've got the jets streaming out, are there any measurements they can do on width or height or something to give information
Yeah, so as you saw in that artist depiction, there are these jets that seem to be coming out of black holes. And is there anything that we can learn based on measurements of those jets? Well, one question that you might have is, why are there even jets? And that's, the exact details are beyond the scope of tonight. But what happens is, as the gas continues to spiral in, and it gets heated more and more, it turns out that powerful magnetic fields are at play towards the center of the accretion disk. And so it turns out that even though you would expect most of the material to fall in, there's actually a substantial amount of material that gets ejected along the polar directions. And so we see you have to have stuff falling in for there to be material to get ejected as jets. And so for solar mass black holes, so those 10 solar mass black holes, the 20 or 30 solar mass black holes, most of the time there isn't that much material, although we have observed certain relatively small solar mass scale sources that are ejecting material. And for the most part, you can't really detect much from them in the optical, other than the fact that they're flaring. But in the radio, it turns out that with radio interferometry, where you string together multiple radio dishes to make very high resolution observations of the radio emission from the black holes, you actually can get a sense that there is this jet-like material. And that paper that I mentioned for Cygnus X1, where they determined that it was about 21 times the mass of our sun, that was based on radio observations. And if you look at the paper, one of the figures of the paper clearly shows this kind of cigar-shaped emission, radio emission, coming from the jet. And so, from those observations, you can definitely deduce mass, temperature, the conditions that result in that radio emission, and so forth. Now, there's another category of black holes that I didn't really talk about at all, which are the supermassive black holes. And so these are black holes at the centers of galaxies. So our Milky Way galaxy sports a 4 million solar mass black hole. And whenever we've examined the centers of galaxies or of other galaxies, it turns out that they, if we observe them very carefully, look at the motions of stars, look at the motions of clouds, they also all seem to suggest, to support the evidence that they have supermassive black holes as well. So it appears that supermassive black holes are a consistent feature of pretty much all galaxies. And it's still a mystery as to how these supermassive black holes got to be where they are and how they got to be so massive. Because clearly, they probably didn't start or evolve the same way that the stellar mass black holes did, because there wouldn't have been enough time for them to start off so small and then just slowly gobble up matter to grow to their current size. So there's a lot of theories around the supermassive black holes, but because there are so many of them, we observe them in other galaxies. They're actually easier to study in some ways than these ordinary mass black holes. There are far many more of them, thousands and thousands, millions of them that have been observed, whereas we have only a few dozen for the stellar mass black holes. Yes, sir. How do we know the Milky Way is a spiral galaxy? That's an excellent question. We live inside the Milky Way. We think the Milky Way is 100,000 light years across. So it's like living in Denver and trying to map the whole city, or maybe even map the entire state, while you're stuck at one spot inside the area that you're trying to map. Well, again, I'll only be able to give a very cursory explanation of this, but it's based on both our observations of other galaxies as well as observations of our own Milky Way. So we can observe other spiral galaxies. We can observe not only the stellar distribution, the distribution of stars, but also how the gas and dust is distributed. And so it's hard to observe stars in our Milky Way because gas clouds block the starlight, but it's easier, depending on the particular wavelength, to observe hydrogen gas, molecular hydrogen gas, and other species. Carbon monoxide is another tracer that we can trace out the spiral arms, and we can trace out the other gas populations. And it's from a combination of all these different types of observations that we can be pretty sure that the Milky Way is a spiral galaxy. Great question. Yes?
I have a question about the brown dwarfs. What do they do when they die? Like last month we talked about neutron stars and how they form by collapsing. What happens after the brown dwarf runs out of deuterium or whatever?
Yeah, so what happens to brown dwarfs when they eventually, they run out of deuterium to burn, so they're no longer producing heat from the deuterium burning? Well, what happens is they'll just continue to cool off. So we saw in that diagram, you had brown dwarfs that were 1,000 degrees or 2,000 degrees, 1,000 degrees, 500, 400 degrees. And basically, you'll expect them to just continue to cool off. And as they cool off, as they emit radiation out into space, that radiation gets lost, the temperature goes down more and more. And I don't know how long it would take, presumably perhaps billions of years, but at some point, they'll reach the absolute lowest temperature that they can reach, which is a few degrees above absolute zero. That's because the universe is bathed in this radiation that's about equivalent to 3 degrees above absolute zero. And so that's basically the coolest that you can be, because if you cool off any further, you'll be reheated by the cosmic microwave background radiation. So basically, these objects will continue to cool off unless they are swallowed up by some other object for some reason, or if a brown dwarf is in orbit around a star that goes supernova, that exploding star could destroy the brown dwarf if they orbit close enough. But if there's nothing else to distract them or disrupt them, the brown dwarf will just continue to cool, and they'll also become more and more difficult to observe as they keep cooling. Yes?
Why are brown dwarfs called brown dwarfs when they're not even brown?
Okay, that's a really good question. Why are brown dwarfs called brown dwarfs even when, though they're not brown? Do you happen to know what color brown dwarfs are?
No.
Okay, you don't know what color they are. I think the reason why brown dwarfs are called brown is because we have stars that appear to be of different colors. So, we think of the sun as sort of a yellow star, but it turns out that the maximum peak in its emission is actually closer to a color that we think of as green. And when we look out into, if we were to observe the sun through filters, the fact that we've evolved as a species to live under a sunlit sky means that sunlight should appear white to us. And so the reason why we think of the sun as a yellow star is because the cooler stars are known as red stars because they do emit more in the red, and hotter stars, much more massive stars that glow hotter, they emit more energy. They peak towards the blue part of the spectrum, and the hottest stars actually peak in the ultraviolet. And again, if you were to add up all the light, they wouldn't necessarily, they might appear kind of bluish white, but they would definitely appear whitish. But people often call them blue stars, even though if you looked at them, through filters that took out light equally, and if you weren't blinded by looking at them, they would appear whitish with a hint of blue, but they definitely wouldn't appear, cerulean, or they wouldn't appear cyan. And so brown dwarfs were called that because you have blue stars, you have yellow stars. Even though the sun peaks in the green, I guess astronomers thought it was so ridiculous to call stars green. Nobody ever proposed making a category of green stars. You have yellow stars and you have red stars. And so the question was, what do you call a group of objects that were cooler than red? And so they kind of went to brown as an adjective, as a color, even though, as it turns out, that depending on how warm that brown dwarf is, what the temperature is, what and its evolutionary history and the amount of metals or heavier elements, some of these brown dwarfs might be brownish, or they might be orangish or reddish, like you would expect from the giant planets. But some of them might actually also be purplish. So it turns out that depending, again, on the circumstances and the material makeup, you can have these kind of weirdish colors that are not really brown, although some of the brown dwarfs are brown. But great question. Yes, in the back.
When you have two stars that are orbiting each other and one goes supernova, why isn't the other one destroyed as well?
Yeah, so the question is why doesn't the second star in a binary system get destroyed if the other star goes supernova? I'm guessing that you can probably come up with, there are probably some scenarios where perhaps a star might get destroyed, but I think for the most part, the star is just too massive to be affected that much by the supernova explosion. So it turns out that when you're looking at massive stars, it's actually more likely for a massive star to be found in orbit around another massive star than it is to be by itself. And the more that we observe, it seems like it's even more, in some cases, it's also very likely for 3 massive stars to be in orbit around each other, or 4 massive stars. So as opposed to a massive star with a star that's much, much smaller than itself. So there's some formation process, or the process of formation biases towards massive stars forming close to other massive stars. And a really good example of that is the trapezium cluster in the Orion Nebula, which is responsible for lighting up the Orion Nebula. And that's 4 stars that are in close proximity to each other. But when astronomers took very careful observations of some of those massive stars, it turns out that at least 2 of them, I think, turn out to be multiple stars in orbit around each other, but they're in orbit so close that we couldn't tell that they were multiple stars as opposed to 1 star. So for the most part, it seems like massive stars tend to form close to other massive stars, and so when you have a massive star, it can withstand a supernova much better than a much smaller star like a brown dwarf or a red dwarf. So it turns out that we do find lots of examples of these binary systems with the black hole or a neutron star, and it's pretty clear that the other star is a giant star. Yes?
Back to like black holes, and I might say this a little wrong, but in the Lanica supercluster, which is where our Milky Way also resides,
Mhm.
right? I've heard of something called the Great Attractor. Is that rumored to be a black hole as well?
Okay, so the question is about, you heard about the Laniakea cluster. So there have been, so one of the discoveries that we made in the last half century, or more actually now, is that galaxies aren't just floating out there alone by themselves, but they are clustered together by gravity. And these clusters themselves could be clustered into superclusters. And so, I often talk about the Virgo supercluster as being our local supercluster, but more recently, in the last 10 years or so, there have been discoveries that show that there's actually this much larger cluster called the Laniakea supercluster that Virgo and our local group of galaxies are all part of, this giant sheet or cluster of galaxies. And so you had also heard about something known as the Great Attractor, and the Great Attractor is actually one of these other superclusters that had been given a name, just a large grouping of galaxies that showed up in surveys, and it was so large that astronomers just they gave it this name of the Great Attractor because it was large enough that you would expect clusters of galaxies to fall towards. And I don't actually know the relative position of the Great Attractor versus Laniakea and a lot of these other superclusters. Hercules has a supercluster, for instance. But they're called the Great Attractor not because of supermassive black hole, but just because of the fact that there's so many galaxies that are grouped together that are identified as being gravitationally grouped into this supercluster. Now, granted, we think that we suspect that all these galaxies do have a supermassive black hole at their center. So there are definitely lots of black holes, but the black holes make up a small fraction of the mass of each of these galaxies. So even black holes that MED7 is a giant elliptical galaxy. I think its central massive black hole is on the order of tens of billions of solar masses, but the galaxy itself is like 1 trillion solar masses in size. So even the most massive supermassive black holes are a small fraction of the mass of the galaxy. So in none of those cases would you expect the black holes to dominate the mass. Yes?
So if we're talking about a brown dwarf star having a moon orbiting around it, why wouldn't that moon be considered a planet?
That's a really good question. I mean, is the moon of a brown dwarf considered a planet or a moon? And I think a lot of people, because brown dwarfs are not considered stars, so the question is something that orbits a brown dwarf technically a moon of a brown dwarf, or is it like a subplanet? And I don't think people have given it enough thought to argue one way or another. And there is also, despite what you've seen from there's the IAU definition of what a planet is, which kicked Pluto out of the planethood that you might remember from 2005. But the problem with that definition is that the IAU definition actually excludes any planets that don't orbit the sun. And so right now, there isn't any one definition of planet that's acceptable to everyone. And we're so far away from really talking about moons or other objects orbiting around brown dwarfs that I'm not sure people have really started to argue about this sort of thing. Although it does turn out that there are surprisingly a large number of brown dwarf binaries. So I mentioned the Orion Nebula a few minutes ago, and it turns out that observations of the Orion Nebula have actually shown a lot of brown dwarf binaries, where the brown dwarfs appear to be roughly similar sizes. So they're not something much smaller orbiting around something much bigger, but they're roughly comparable in size. Let's say 20 Jupiter masses versus 40 Jupiter masses. And so they must have formed together, but right now, because no one had had a theory that predicted lots of binary brown dwarfs, they're kind of an unexpected surprise, and the theorists have now had to go back to the drawing board to try and figure out how you can form a lot of brown dwarf binaries. So that's the only other example you have a brown dwarf orbiting something else, is another brown dwarf. But this is currently, so far, it's indirect evidence for a moon. It's not, they haven't clearly said, even in the paper, that they think it's definitely a moon, but it's definitely one of the possibilities. All right, maybe one last question.
Yeah, you mentioned something about super huge stars in clusters orbiting each other, like, 4 or 5? I would assume that if you had really large, massive stars in a cluster like that, they would be very unstable and kick each other off until they went down to binary systems. Chaotic orbits.
Mm-hmm.
Can
Yeah.
you have stable orbits like that?
Yeah, so the question is, is it possible to have stable orbits when you have these multiple stars, multiple massive stars that are in orbit around each other, whether it's a triple star system or a quadruple star system. I guess the quintuple and sextuple systems are the ones that I'm aware of. They don't involve massive stars, but I don't know enough massive star multiple systems. From what I guess my answer to that is, whether these systems are stable or unstable. I actually don't know enough of that to answer your question. They're apparently stable enough for us to find examples of lots of these systems. And even if you have a quadruple system, what you might have is you might have 2 stars that are in tight orbit around each other, and you have another 2 stars that are in tight orbit around each other. But those 2 pairs are in orbit far enough apart that they can't disrupt one pair can't disrupt the other pair. If you have a pair of stars that are in orbit each other and a third star that's in orbit much further apart, then that's also a scenario where you can't disrupt, that third star can't disrupt the close binary. But if you have a pair of stars that are in orbit each other and another one that's orbiting a lot closer, or perhaps it's orbiting even closer around one of them, then you can imagine scenarios where just from these gravitational interactions, you can get these chaotic situations where, as you say, one of the stars actually gets kicked out of the system, and then the remaining stars end up orbiting even closer together. And so I would say that for those systems where something like that is likely to happen, it's either about to happen or perhaps it's already happened, and you have a much stabler system as a result. But as far as what fraction of massive star multiple systems that are like that, where it appears like they're in this chaotic situation or they're about to kick another member out, I don't actually know what the statistics are. I just know that these things can happen, and you can settle into these stable states. But what fraction of those are stable states versus systems that are potentially unstable, I don't know. But good question. All right, well, thank you everyone for coming, and hopefully I'll see you next month.